is Sean, and I'm the founder of Polito Labs, where we're thinking about fundamental problems in the blockchain space relating to interoperability, scalability, and privacy. So today I'll be talking about some of these ideas in relation to scalability and interoperability. Um, they're called cryptoeconomic coprocessors. So first, I think we'll just disambiguate what's a coprocessor, and we'll just kind of see what are the types of coprocessors, and then we'll hone in on the cryptoeconomic part of these coprocessors. So let's begin. So we have generalized computing. These are like CPUs. They're great. You can run any kind of program on these things, and for most applications, this is perfect. But for some kinds of applications, this doesn't scale. And so we have coprocessors, which are just specialized hardware that allow you for accelerated computing, right? So you can do things like sensor data, you can do things like GPS data, you can co-process graphics, and there's even more esoteric stuff, like you can actually program a hardware element to be more optimized for some specific computation on the fly. So these are FPGAs. And so this is what that looks like, right? You have some CPU, it hosts some computing element, but it's unfortunately insufficient, and so you extend it with a new hardware element. For instance, this could be the GPU, this could also be your maybe image sensor coprocessor. But what does that have to do with blockchains? A coprocessor essentially is a way for us to extend the computational capability of a blockchain, and this is because blockchains are fundamentally limited by laws of physics themselves. You can't keep shrinking these transistors. You eventually run into quantum problems where the electrons essentially tunnel through silicon hardware, so we're limited fundamentally. There's no infinitely scalable blockchain. And so we want to be able to perform this computation outside of the blockchain, but then return the results of this computation with some proofs. And this is what this would look like. You would have some blockchain, it's isolated, but then you have this sort of specialized thing that's outside of the blockchain itself, but it's still communicating with the blockchain. It's receiving tasks, it's reporting back the results of these tasks, and you have some proofs for this. And this is what this would look like. You would have some input, and it goes into the coprocessor. The coprocessor probably already has the required program to run. It runs the program, it generates the outputs of the programs, and you have a proof, right? So because we can trust the computation that was done. And I think it's really important to have proofs, because when you don't have proofs, well, essentially you've created an oracle. And I think we're at Web3 Summit, we are all fans of verifiability. And so I think a coprocessor is the fine thing that separates us from trust and truth. But the more sophisticated of you might say, well, this is just a snark, right? Like, you're not really inventing anything here. A snark will already take some inputs, they have some outputs, and they give you a proof. Actually, this is not correct, because a snark doesn't actually take any kind of inputs or outputs. What you have is a private witness. We call this the execution trace, or essentially all of the variables in your program and kind of how they changed over every cycle of execution. And then you can put that into a snark, and the snark will generate a proof that this execution trace describes a valid program, right? And so you don't have outputs, actually you have inputs to the snark. And then the snark says, well, this input for the program that we both know does generate this proof. And so these are called ZK coprocessors. They have some really good attributes in that they produce very, very small and cheaply verifiable proofs of computation. In fact, you can also take a step further and aggregate proofs across many ZK coprocessors into a single proof, the so-called proof singularity. So if this is all well and good, why don't we see any ZK coprocessors today, right? Well, and maybe one more thing about ZK coprocessors is that they can also hide information about the witness, like I described earlier. So you can actually have what we call private computation, and you only reveal parts of the computation that you care about. But we go into why we don't see ZK coprocessors. Well, they suffer from what we call asymptotic slowdown. So an algorithm run natively on its own probably takes 10 minutes. Same algorithm in a snark, you're looking at an hour, 10 hours, depending on how much computation that this algorithm needs to do. So as a result, it's very expensive. And yeah, sure, we can do like proof aggregation. Maybe we parallelize this computation across multiple instances, and then at the end of the day, we just recurse into one proof. That's not free. You essentially now have to do n minus one extra proving steps. So if you had run n instances, you now need to do n minus one proving steps. And the reason for this actually is because of the structure of a ZK circuit itself. You can't have arbitrary inputs. You always have to know the number of inputs into a circuit. And so at the base case, you define maybe a simple circuit. It takes two proofs and two private inputs, aggregates that proof into a single proof, and then maybe the public input is the hash of the two private inputs. And essentially, you can then build a Merkle tree of these proofs, right? And so at the root, you have some hash of the public input, and that kind of attests to all of the private inputs, public inputs at the bottom of the tree. And as you can see, this is 8 elements, but now we have to do 7 extra steps to arrive at the root proof. And there's still some other stuff. Well, essentially, this is a lot of computation, and this is, for efficiency reasons, best done by a single person. I know there's people talking about prover markets, but the truth is, if any one person has all of the computation, they can essentially undercut the cost of this computation every time, essentially starving out any other person who's trying to be part of this prover network. It's also not well suited for cryptographic computations like cryptographic hash functions or elliptic curve pairings. This is because all of your variables have to essentially be binary decomposed into the circuit. I'm getting a bit technical here, but essentially you are extending the size of your circuit, creating more prover work. And it's also not easy to audit. There's been bugs of live ZK systems. Halo 2, ZK Sync, they've had bugs in their circuits. So these things are immensely difficult to audit, and this is just one of the many problems. And so maybe we can say it's better suited to what we call client-side proving, where essentially we're not trying to create a ZK proof of some global computation. Maybe there's just some local computation that needs to happen, and we're able to do this very cheaply in a browser, on a mobile phone, and it's private, right? So you can build peer-to-peer privacy payment protocols or whatever, or what have you. But then, okay, we can't do ZK coprocessors for global compute. What can we do? Well, there's a new kind of coprocessor, which I will introduce as a crypto-economic coprocessor, which is basically a blockchain, right? It's blockchains are also verifiable computing. In fact, the blockchain was the first verifiable computer before we then had to invent snarks. And if you have a programmable blockchain, then this is a general purpose verifiable computer. And how are they verifiable? Well, they're verifiable through what we call crypto-economic proofs. But this is not a new idea. Actually, this is the slide from Gavin Wood's first talk at DEF CON, where he introduces, what is Ethereum? Well, it's a computer that is verifiable and auditable. But even further back than Gavin Wood is the Bitcoin white paper, where Satoshi essentially describes that it's possible to verify the work that a blockchain is doing. Of course, he says specifically here payments, but in general, you can verify any kind of computation that is done on-chain, where a verifier just needs to keep a copy of the headers and what is the consensus proof, right? What is the cryptoeconomic proof that these headers are final or in the longest chain, whatever your consensus rule is. And so consensus proofs, well, essentially, in order for us to have this notion of a single chain, we need cryptoeconomic guarantees, whether that's a lot of work that has been expended on the honest chain, or whether that's a significant amount of capital that's backing the longest chain. And yeah, Nakamoto says, well, this would be the longest chain in a proof of work system, whereas we have proof of stake nodes that just bond tokens with security. And then these consensus proofs in general, they attest to what is the header. So a header is just some metadata about a block, its previous hash, its number, and something we will call a state root, which takes us into what a state proof is. So essentially all blockchain state, your contracts, its storage items, your balances, they're all stored in what we call an authenticated Merkle tree. And the root of this Merkle tree is put into the block header. So for those of you who have some ideas about Merkle trees, you know that this allows us to authenticate parts about the tree without essentially revealing the full tree. And this is good, especially when you want to learn about parts of a blockchain state. And so this is what the Ethereum world state looks like. And it's just basically a Merkle tree. And this is where all your contracts and all your balances live. And you can see that in any of the headers, you can always arrive at some state root that represents the state of that blockchain. So back to how we verify these cryptoeconomic coprocessors, well, we essentially need to perform consensus verification. We have some header that tells us that some computation, if you think about a block as a snapshot of some computation, and we have a proof for that, and then we're able to read the results of this on-chain computation using state proofs. So back to our initial diagram, we no longer have this snark. Instead, we have a blockchain. Its inputs are transactions, world transactions. Anyone can submit transactions to this blockchain. Its outputs are in its on-chain state because it doesn't have any ability to dial TCP or something. Applications only mutate the state. And then the proof that what was done on-chain is correct is this combination of this cryptoeconomic proof, the consensus proof, and this Merkle proof of those items in state. And now we have a verifiable computer made out of a blockchain. Yay. What can we do with it? Well, let's look at some of its pros. I think this is a very philosophical thing, and I think we're all very familiar with this, is that block space is infinitely abundant. There's now so many blockchains, and they're all mostly subsidized. If you look at the ultrasound money website where the supposed profitability of the Ethereum network would have been tracked, it's now going the other way, especially with the launch of EIP 4844. So block space is basically cheap. It's almost free. And in these kinds of coprocessors, these computations, they run at native speed, right? They're running on the node software. They're not, they don't suffer from any kind of slowdowns. Maybe if you put them into a virtual machine, then you might have a little bit of a slowdown there, but it's not going to be as bad as a snark. And this proving time is interesting, is that we don't have any proving time. Proofs are cryptoeconomic proofs, right? And they are generated by finality. So if you have a blockchain that has very fast finality, then your proving time is as fast as this finality. And they're also very easy to audit. So because essentially we're writing native Rust or we're writing native Solidity, we have experience auditing these kinds of programs. And I think the last thing is that blockchains are inherently decentralized and are, by that design, resistant to regulatory capture or any kind of censorship. Whereas if you had a ZK system, because of this centralized entity, they can become targets for regulatory measures or any kind of censorship, and we've seen this happen multiple times. So they have some, drawbacks. Well, you can't exactly try to use them for private computation, and they must have very high economic security. So this is where the crypto economic part comes from, is that, well, if you have a blockchain that has maybe $10 of economic security, you can't exactly try to pass that off as a verifiable computation. You must have at least as high of a few $1 billion of security for us to be able to then make some assumptions about what is the cost of breaking the security. They should also have cheap consensus proofs, which is pretty easy. You just do BLS signatures. And they should have cheap state proofs, which can come from maybe binary Merkle trees. You don't have to use the inefficient Merkle-Patricia tree that the Ethereum blockchain uses. And ideally, they should be parallelizable, whatever that means. I won't go into this, of course. Okay, so let's look at some of the applications of these kinds of coprocessors. One thing that I really, really like about this construction is that with these kinds of coprocessors, we go from a user-centric view of blockchains, where previously we had built blockchains for human beings to use and coordinate and build their shitcoin applications on top. But now we go to this service-centric view of blockchains, where actually a blockchain should provide services to other blockchains, whether that's compute, whether that's data, and actually we'll see all of these applications. So first I would think is the notion of an interoperability coprocessor, which, well, the problem of interoperability has always been that we want to have a way to authenticate messages between blockchains. If we introduce a third party that does this authentication, then this is basically an attack vector. And so even more so, once we're able to authenticate these messages, we then need to aggregate them, right? So that we can have a single proof to any blockchain that tells that blockchain the aggregated messages that it's interested in. And so the computation that's needed to do this aggregation, it's actually already been done today by Polkadot. I think Polkadot's really the only kind of this coprocessor, but also Hyperbridge, which will soon be live. And I was going to go into maybe a little bit of interoperability here, but I think I just want to show this image where you have a coprocessor that is able to aggregate messages from all of the different chains and is then able to distribute these messages to wherever they need to go to. And you do so by doing this consensus proof verification as well as state proof verification. But what are the other applications of this? Well, there's also this idea of a state coprocessor where you can essentially take on-chain state pricing, Uniswap pricing data, or maybe information about what on-chain accounts are doing, what transactions they're making, and you can then construct more useful data out of these pieces of data, right? You're refining this on-chain data. You can construct a TWAP out of pricing on Uniswap and then use that in lending protocols or any kind of money markets, right? Or you can have on-chain reputation systems that essentially, take information about what accounts are doing on-chain and then compute some reputation for them. You can also have data availability coprocessors, and I feel like these are not new. Essentially, you custody some data on behalf of some blockchain, whether that's L2 rollup data or whether that's a movie, the B movie, and then you are able to provide liveness guarantees about this data. So that's why it would have to be a blockchain, is that a blockchain can have some notion of liveness, and you're able to prove that you have this data at any point in time, right, with a live client. Other applications would be, ironically, ZK aggregation coprocessors. So like I demonstrated earlier, it's actually very inefficient for you to use ZK to aggregate ZK proofs. And so what some people are doing is they're going to use a blockchain to aggregate these ZK proofs and then present a much cheaper proof to any blockchain attesting that these proofs have been verified. And there's a few examples of this today, like Lanlege and ZK Verify. And there's even more crazier ideas like a TEE coprocessor where you can extend the on-chain environment with the ability of the TEE enclave. Some ideas around this would essentially enable sealed bid auctions and maybe on-chain attestations for AI inference way out there. But these are kind of the applications that we're thinking about. I'm not saying that this is the definitive list of applications for crypto economic coprocessors. I think the notion of them is simply on-chain computation that is attested to by consensus proofs and state proofs that allow anyone to authenticate that this exists in some blockchain state, and as a result has then been previously computed on-chain. Then I think the applications are really unbounded. But that has been my talk. I'm on Twitter as Seun, and you can browse our website where we write some of this like philosophically out there stuff. Thank you.